So today we're going to be expanding on the area problem. We've done the area problem previously where we did it along a straight line, and albeit we could figure out the exact value of most of those areas, the area problem wasn't designed for areas that we can use simple geometric shapes for. Triangles, squares, trapezoids, circles, things like that. It's really going to go into what happens when we try and find the area beneath this generic curve, which we'll notice that our equations are going to change into something that we don't really have a nice pretty little formula for. The second thing that we're going to be going over is one of the things that we've done previously, and I think the best way to describe this is to show what we've been doing. When we separate a function into these individual pieces, so let me draw a straight vertical line right here. A straight vertical line right here. When we've been separating this into different pieces, we know that if we use the left endpoint rule versus the right endpoint rule, we're either overestimating or underestimating completely depending on what's going on. We know that if we added some three-dimensional aspect, or not three-dimensional, multi-curve to it, if we go up and then down and then up again, we know sometimes a little bit of those cancel out, but again, we're either drastically over or underestimating. And now what we're going to be doing today is we're going to be illustrating a different approach, and it's going to be using the midpoint. Because with the midpoint, when we estimate our area of the rectangle, yes, we are overestimating on one part of our rectangle, but we're also underestimating on the other. So it offsets itself much more closely to the actual area of the graph, and especially if done over multiple iterations in a small enough delta x, it's a much more accurate estimate, and we don't need to wedge in our previous guesses where we were doing high and lows and we know it's between two values. This is a good estimate if we just want a singular number. So the idea of what we're going for here is how would we illustrate a rule for that? Well, we know with the right endpoints, we always start wherever the function is, and I say, well, the right endpoint is I move over delta x, which is why we plug in delta x that many times. For the left endpoints, for my first iteration, I have to go back to my original. So albeit I start here, I'm adding delta x one less time than my number suggests. So how would I get midway? Well, I would go over one full delta x, and then I would subtract not a full one, but a half one. So our generic midpoint formula is, let's take our f and plug in our a, and we're going to add our delta x however many times we want, and we're going to subtract half of a delta x. Now, this isn't written in the same notation as the other two. The other two, if I distributed that delta x, I would get the same thing. Delta xi minus a full delta x. This is delta xi minus half of a delta x. It moves us back into the center of that. And so the other thing that we want to try and create is, if you are the type of person who likes a generic formula that I can just look at this and plug all my numbers in and move, let's try and break down in terms of a, b, and n. How would I generically solve any one of these functions, any one of these sums where I'm trying to find the area beneath the curve? Well, let's take a look. We know the sum is built off of base times height. I know the base is going to be, if we look at that, is going to be a delta x. And previously what we've done is when we have delta x, we say, okay, what is the average change? What is the average width? And we've said that that is going to be our n term, so b, minus our first term, divided by the number of rectangles. So I can take that and plug that in. Then we know, okay, it's going to be our function evaluated out right here. So it's going to be a plus delta x. Actually, that should be going right here. It's going to be times our function, a plus delta xi minus delta x over 2. And then all we do is we change all three of these delta x's into a's, b's, and n's, and we'll basically have our formula at that point. So this is b minus a over n times f of b minus a over ni minus b minus a over n, all divided by 2. And so I know that if I turn that into a fraction and flip it, I'm going to have my final equation right here, which is going to be the sum from I equals 1 to n of b minus a over n times f. I'm actually going to make this a bracket. Let's see. We could actually attempt to combine these, but we're not going to. A plus b minus a over ni minus b minus a over 2n. Close the function, close the bracket. And there we go. Here's our generic formula. If you want a formula to find the sum of any function from a to b with n rectangles, we can just go ahead and plug this in right here and get that. Cool. But let's go ahead and jump into the first one. So we want to use the midpoint rule in this. So we're not finding a high value and a low value, and we have x squared from 0 to 20 using 20 rectangles. We know the actual area of this using an infinite amount of rectangles is 2,666.7, which means this is going to be a fraction here. And we want to figure out what this would be approximated using the midpoint rule. How close are we? Okay, well, first off, let's find our delta x. So our delta x, remember we said it's b minus a, so 20 minus 0 divided by the number of rectangles. It's going to be divided by 20. So we get delta x is equal to 1. This is going to make our math a lot simpler. So let's go ahead and plug that in. So we know, let's actually do this in purple to keep consistent with them previously, is going to be the summation from I equals 1 to 20 of base times height. And we know that base times height is going to be reevaluated right here. We know the base is going to be our delta x, and our height, let's do that in green, is going to be f of a plus delta xi minus delta x over 2. Awesome. And so let's simplify this so we can plug that into the summation notation as simple as possible. Okay. First off, our delta x we said was 1. So now this is times 1. And this is going to be f of, our a is 0, 1i minus, actually I'm going to keep my delta x's in red just to keep them consistent, minus 1 over 2. I'm going to plug whatever this simplifies down into my f of x. Okay, so 0 minus 1/2. This is just going to be I minus 1/2. And at this point, I'm not even going to write my 1 anymore because I know 1 is just going to keep whatever this value is. So at this point, let's go ahead and plug that in, and let's change colors to show that we have indeed plugged it in. So my f is going to be x squared. So I'm going to take that value, and I'm going to square it. In this case, it's I minus 1/2. Okay. So when we get that, I squared is I squared. Half of an I is going to make a full I, and then plus 1/4. And so what we're at right here, I equals 1 to n, is our first point. In fact, I'm going to draw kind of a line separating it. All we did up here was to simplify what we're taking the sum of. At this point, we're taking the sum from 1 to n, in which case is going to be 20, of this expression. And so now we can come over here and actually evaluate out that expression in the sum rules that we know. Any constants we're going to move out to the front, in which case there's nothing right here, but I am going to have 1, 2, 3 sum terms. 1, 2, 3 sum terms. I'm going to take the sum of I squared, and we are going to subtract the sum of I, and we are going to add the sum of 1/4. All three of these sums are from I equals 1 to 20 for all 20 triangles. Not 20 triangles, 20 rectangles. Perfect. Center this problem up a little more. Cool. And so let's go ahead and reduce this. We know the formula for I squared. Let's actually write these out to the side. The sum of I squared is going to be n times n plus 1 times 2n plus 1, all divided by 6. We know the sum of I is going to be n times n plus 1, all divided by 2. And we know the sum of a constant is going to be the constant times n. So these three formula we're going to plug in over here. So if I have I squared, I'm going to jump immediately into this. So this is going to be 20 times 21 times 41, all divided by 6. Minus summation of I. So 20 times 21 divided by 2. And we are going to add 1/4 of this. So this is just 1/4 times 20. Boom. And so let's see what that reduces down to. At this point, we're probably going to have to pull out our handy-dandy calculator. Cool. So I'm going to take 20 times 21 times 41 divided by 6. For my first term, I will get 2,870. 20 times 21 divided by 2. Subtract 210, and 1/4 of 20 is 5. So 2,870 minus 210 plus 5 is going to give us 2,665 is the rough area. And now we said that the midpoint was going to be more accurate. We are really accurate, even with a width of each of our rectangles of one whole unit. We're not even dealing with a fractional unit. We are about 1 2/3 off, so 1.7-ish off. That's very close. That's a very high degree of accuracy in percentages, especially dealing with such a big number. That's a really good indicator, which is why the midpoint is generally used for these summations. But let's go ahead and let's try another one. Now, we said that one of the other things that we wanted to practice was plugging in multiple values of x. So far, a lot of the equations are very, very simple. What would it look like if I had to plug in something a little more complex? Well, I know that this summation should give us the actual area of 5,433.3, or again, this is going to be a fraction. So let's give this a shot. So if we want to find our delta x, I'm going to do the same thing as before. I'm going to take 20 minus 0 and divide it by the number of rectangles. So 20 divided by 40 is 1/2. So my delta x is 1/2. Cool. So let's pop in right here. We know that we are summing from 1 to 40 because we have 40 triangles, not 40 triangles, 40 rectangles, all base times height. Okay? The base we know is going to be our delta x. The height, as we know, is we're going to plug in that midpoint each time. So starting value plus delta xi, moved back half a space to get that value in there. So we know this is going to be 1/2 of the function evaluated to, let's go ahead and plug in our values. That's going to be 0 plus, well, delta x is 1/2 of I minus delta x divided by 2. Well, this is 1/2 halved, which is going to, in essence, be 1/4. So our formula that we're doing is 1/2 times the function evaluated out to 1/2 I minus 1/4. Awesome. And so the first part isn't too bad. I have to plug this value into this function. So let's copy out this function and leave some space. Now I'm going to draw a bracket because it's going to take some simplifying to get this down to size. So 2 squared plus 1/2 of that. What are we plugging in? This value. 1/2 of I minus 1/4. 1/2 of I minus 1/4. Okay. And so now the fun begins. Now we get to simplify what this is so that we can reduce our sigma notation. So I'm going to draw a dividing line right here because we're going to start simplifying this in its own section because I doubt we can do this in one step. So we have our 1/2. First thing we're going to do is we're going to square this. We know the generic rule for this is going to be I square the first term, so 1/4 I squared. I multiply the 2, that's negative 1/8, and I double it. So 2/8. So 2/8 is going to reduce down to 1/4 I. And then square this, so minus 1/4 times minus 1/4 is going to be plus 1/16. Then I'm going to distribute this 1/2, so this is going to be 1/4 I minus 1/8. Close my bracket. Cool. So I'm still trying to simplify what I'm plugging into my sigma notation. At this point, it's just a lot of algebra. So let's go ahead and check this out. I'm going to distribute my 2 into here. So 2/4 is going to be 1/2 I squared. 2/4 is going to be 1/2 I. 2/16 is going to be 1/8 plus 1/4 I minus 1/8. Cool. We get a few things that'll cancel out. What color do I do this in? Let's do it in black. Plus 1/8 minus 1/8. And then I'm going to combine these two. So minus 1/2 plus 1/4. So that's going to be 2/4 plus 1/4. That'll end up being minus 1/4 I times 1/2. And if I combine all of this together, let's see, what color did we do previously? We kept it blue, so let's keep it blue. Actually, no, let's switch over to black because now we no longer have base and height. We're going to combine this into whatever base times height is. So this is going to be 1/4 I squared minus 1/8 I. There's the sum that we're taking. From I equals 1 to 40. So again, the process wasn't too bad. It's base times height. We know what our base is. We know how to find the height. We just got to plug it in and simplify it. So boom, we're going to take this and see what this approximates down to. I'm going to draw my line. I know because there's two terms, I'm dealing with two sums, sum 1 and sum 2. I know that for sum 1, I'm dealing with I squared. For sum 2, I'm dealing with I. I'm going to move all the constants out to the front. So this 1/4, I'm going to place in front of this, and this 1/8, I'm going to place in front of this. Both of them deal with 40 rectangles. Boom. And so now we're going to use our formulas to simplify these. I know I'm dealing with 1/4 because this is a squared term. I know it's going to be n times n plus 1 times 2n plus 1, all divided by 6. Minus 1/8. Because this is an I, it's going to be n times n plus 1, all divided by 2. Cool. Now for the easy part. For the first one, we have 40 times 41 times 81 divided by 4 divided by 6. We get a value of 5,535, and we are subtracting 40 times 41 divided by 8 divided by 2. 102.5. So 5535 minus 102.5 is going to give us a value approximately 5,432.5. We are really close to our estimate. So again, this dealt with a large value, a complex equation with a lot of rectangles, and we are, in essence, less than 1 unit off in our estimate. These aren't crazy small rectangles. This is just a rectangle with a width of 1/2, and we're within one value. So, pretty good estimate. And so now that you've seen 2 examples, why don't you go ahead and pause the video on number 5, try it out, unpause the video, and see how well you did. See if your approach was accurate. The only difference here is that, yes, we're plugging in a value, but you'll notice that we're not starting at 0, so keep in mind that your A term is going to be slightly different. And know that this value, summed over this span, is going to be equivalent of 45.3. So go ahead, pause it, unpause it when you're done, and see how you did. Okay, so let's see. So we know we're dealing with a sum. I know my sum is going to be from 1 to, in this case, 100 rectangles. Boom. So we're going to have a big old thing. Base times height. I need to figure out what is the base and what is the height. Well, I know the base in this case is going to be delta x. And the height is going to be all these midpoints. So a plus delta xi plus delta x over 2. In which case, I need to figure out what is delta x. So let's get this. So delta x is going to be 6 minus 2 divided by 100. So 4 over 100. So each rectangle has a width of 4 100ths. Makes sense because the total width is 4 divided by 100. If you want to reduce this down to 1/25th, you can. Sometimes I like to keep it as 4 100ths just so I can keep in mind what exactly that is. That is the width. But 1/25th. Let's give this a shot. 1/25th times my function where I'm plugging in 2 plus my delta x is 1/25th. I'm not adding, I am subtracting this. Minus 1/25th divided by 2, which is going to be 1/50th. So 2 minus a 50th, that's going to be 100 minus 1, because 2/50ths is 150s. So that's going to be 99/50ths plus 1 over 25i. Cool. This is going to be some gnarly fraction work here. So let's go ahead and plug that in. I got 1 over 25. And let's write out this function right here. I'm plugging in this value. So 1/2 of this squared plus 20. That's my height. That is 99 over 50 plus 1/25th I. Probably should be writing that term in front, but oh well. Cool. So that gets to the point where we're going to go ahead and we're going to simplify what is that going to be. So my simplifying what is that going to be is going to happen right here. So our first step is to square this. Okay, so I'm going to square the first, which is going to be 25 squared is going to be, I believe, 625. Yes. So off camera, what you see me doing is checking my basic arithmetic because, yeah, 25 times 25 is 625. I squared. I'm going to multiply these two together. So it's going to be 99 over whatever 50 times 25 is. So 99 divided by 50 times 25 is going to give me my numerator or denominator. So 1250, and I'm going to double that times 2. Boom. 99 over 625. Yeah, that's positive. And then I'm going to square that. So 99 squared is going to be 9801. Yes, and we are adding this. 9801 over 620. Nope, that's over 50 squared, which is going to be 2500. So that is that value squared plus 20. Oh, this is going to be fun. So I'm going to take half of all of this. Okay. So half of 625. Let's see, what is 625 times 2? Let's get this into focus so we don't, because we're going to be using this a lot. So 625 times 2 is going to be 1 over 1250 I squared plus, oh, yeah, we just did that, plus 99 over 1250 I, 2500 times 2 is going to be 5,000, so 9801 over 5,000. Okay, the next thing I'm going to do is I'm going to combine these two terms, so 9801 over 5,000 plus 20. So let's take a look. What is 20 in terms of 5,000? 100,000 plus 9801 is going to be, it's going to be 109,801. I think at this point it would be really nice to use some decimal approximations, but we know that would throw us off. And this is going to be 109,801 over 5,000. Multiply all these by 25. And so this is going to give us our fabled thing that we need to figure out. So 1250 times 25 is going to be 1250 is going to be 99 over 31,250 I. 5,000 times 25 is going to be 125,000. Awesome. Now, these do look like some gnarly fractions, but we notice it's the same process, the same number of steps as the previous one. The only thing we're noticing here is that from 1 to 100, this is going to be a very accurate estimate. So let's go ahead and take this and convert this into the sigma notation that we can simplify. I'm going to draw my line. I'm going to come over here. I'm going to move any of these out to the front. So I will have 1 over 31,250 times the sum of I squared. I'm going to have 99 over 31,250, of the sum of I. Plus weird sigma notation, 109,801 over 125,000. Boom. So we get that. Okay. We can then reduce this into our formulas. So 1 over 31,250. So I squared is going to be 100 times 101 times 201, all divided by 6. For a regular I, it's going to be n times n plus 1, all divided by 2. And for our last term, it's just going to be 109,801 over 125,000 times n. Boom. Now, albeit that was a little grueling, we can notice that it looks exactly the same as what we had previously. Now, the fractions are a little more outrageous, but we noticed that with 40 rectangles, we were within 1. With 100 rectangles, we should be really close to that 45.3. So let's evaluate what this will give us. Okay. So we have, let's clear this, 100 times 101 times 201 divided by 6 divided by 31250. It's going to be that. Is that a fraction? Yeah. We're going to leave it as a fraction. That's a terminating fraction, but just in case they weren't terminating fractions, let's leave it as a fraction. And we are adding 100 times 101 times 99 divided by 2 divided by 31,250. Again, that does look like a terminating fraction. I don't know why that's a funny terminating fraction, but noted. And then I'm going to take 109,801 times 100 divided by 125,000. Perfect. I'm going to add those three things together. So plus 999 plus we get this. Okay. We get 114. Boom. And there we go. Double check our work. There we go. So I'm going to go back and I'm going to check this because we should get something that's very, very, very close. As of right now, I'm assuming that maybe I typed something in wrong when we checked that. But what we've got going on right here is it's 114.6664. And yes, that was a typo. So it's not 45.3, it is roughly equal to 114.6 repeating. So what we look at right here is that our actual area is 114.6 repeating. We got 114 and we got 3 6s. So we are within 1, 2, so 10, 100,000, 10,000s. We're within 2 10,000ths, so 1 5,000ths of a value with 100 rectangles. So we're really, really close on this. And there you go.